I'm Will Clemens, and I'm from DIDA, and I'm going to present this project we did on detecting defects in semiconductors, or semiconductor lasers in particular. And this thing is called LaserSKI, and it's a sort of collaboration between DIDA, who I work for, which is a machine learning company, and a bunch of hardware companies funded by the German government through the BMBF. And in particular, I'm going to talk about the work we did on the data from the FBH, which is an institute in Berlin that makes semiconductors. So first of all, I'll talk about DIDA, the company. So we are a small but growing company in Berlin that does sort of machine learning consultancy and small custom bits of software. We about 30 people now, and kind of the philosophy is to try and be a bridge between research and sort of business or public institutions that need machine learning. Okay, so I'll just have a brief overview of what we'll talk about. So first of all, I'll give a really short introduction to what a diode laser is. I'll kind of explain the problem and show you some data, some example data. I'll show you how we solve the problem, which is a faster RCNN, which is a pretty standard object detection model, and then show some results and sort of possible extensions and conclusions. Right, so a laser is, this is something before this I hadn't thought about since my undergrad physics days, but basically a laser stands for light amplification through stimulated emission of radiation. And to get a laser, you need a system that can be in two energy states. And what happens is you get a photon that comes along, and if the photon is the same energy as the gap between these two states, it can knock the system down into the lower state, and you get two photons. And basically, this process lets you build up quite a strong and, most important, really coherent light source. And in a diode laser, which we'll talk about now, this is achieved by using a what's called a p-n junction. So a p-n junction is two semiconductor pieces, one which has the current is, it's a p-type, which the current is carried around by sort of holes where there are a gap of electrons, and an n-type, where the current's carried around by extra electrons. And if you have these two materials next to each other and you put a current across it, you can produce this effect with the two energy states. So this is basically what a diode laser looks like, and this works. P-n junctions are actually used everywhere in semiconductors, and LEDs are p-n junctions and lots of other things. But the diode laser we have here, this is the important takeaway for our point of view, is that there are, is the geometry. There is, the top of this is called the P side, and the front and the back are called the facets. And so we basically will have kind of two modalities of data, one for looking directly on top of this, and one for the two ends. So the goal we have is we're going to get some microscope images of these samples when they're in production, and we want to find and classify defects on those. So this is the inspection setup that FBH have, and we were able to go to visit this. This is in a clean room, and we had to wear coats and hairnets and everything to go in. But you can see this is samples here, and it's on a kind of rotating mount. So at the moment, the microscope is looking straight down at the P side of these bars, but then it can be rotated in the two other directions to see the front and the back. So here's some example images. So we have the facet and the P side, and the facet is quite a much higher magnification than the P side. And you can see this is the end of the bar, and the end of the bar is normally quite bad, so this is obviously quite a bad bit. This is not in the middle, and you can see there's another defect here. And the P side has a lot more structure, these are obviously very large images as well. These are especially this facet is cropped, but this comes as a single giant thing. Yep, so the way we're going to solve this is we train a faster RCNN, which is a object detection model, to basically draw a box around each individual defect. And yeah, this is how what a faster RCNN looks like. You have you take some features from a standard CNN, which you can get a pre-trained one, and then fine-tune it. And we take features from feature maps from different layers, and concatenate them together to get basically a feature map that represents for the early layers, which have sort of small and low-level information, up to the deep layers, which kind of include broader, larger scale and kind of more abstract information. So these are concatenated together, and we use what's called a region proposal network that proposes different potential candidate bounding boxes, and then these are classified, and one of the possible outcomes of the classifier is to reject it and say there's actually no box there, and also a bounding box regressor kind of fine-tunes the sort of exact geometry of the box. And what's isn't really clear here, but it's quite important, is that the model actually relies on sort of predefined anchor boxes that adjusts, and that was kind of important later because it's the source of one of the errors in the facet side. Okay, so yeah, maybe some brief overview of the sort of training details. We implemented it all in PyTorch Lightning. We use quite that's a bit of a typo there. We have quite a large data set labeled by FBHAR, so we have about 250 of these big images, which is obviously quite a lot of samples each labeled, and we have a similar amount on the facet, although I don't know the number off the top of my head there. We trained this on 800 by 800 pixel chunks that we split out so that, with some overlap, so that if something is directly on the edge, it doesn't get missed. And when we reassemble these, that we kind of sew together predictions that are across multiple chunks. And we used a couple of metrics. MAP is a pretty standard object detection metric, but it's not so easy to kind of, it's not so interpretable intuitively. So I think I prefer F1 50/50, which is F1 is this combination of precision and recall that people are used to, and this is with a threshold of 0.5 for the objectness, which is kind of the score of how sure it is that there's a box there, and also the intersection threshold. So you need to define a true detection, you need some threshold on the overlap between the real box and the predicted box. Okay, so here we have some examples of the facet. This is a bit compressed, but so here's an example of there's some very good stuff and some bad stuff here. We predict a lot of these particles, and although we've missed some stuff here and here, and the reason we miss this stuff is because when we're in a very dense region with lots of detections, we run out of these anchor boxes, and the model kind of struggles there. The advantage, though, of course, is that you can clearly, this is one of these sections right at the edge of a bar, and you can, I think you don't need to detect all of them to know that this has got a lot of defects in. So from that point, from a quality assurance point of view, this is quite easy. We have a few more. This is a slightly better one, showing that we don't really miss much when it's not so dense. This one is, this is just another nice one. This one is, this just shows that we can detect very big defects that have to be sewn across multiple boxes. And this one is particularly interesting because I actually thought this was a false positive when I first looked at it. And this is not very well designed for a projector, but you can on the screen slightly see that there's a very faint line, which is this terrace defect, which is when you basically have the surface of the crystal, and then one or a few layers of atoms are stripped off, you get this terrace where you get that step. And it is there, I promise you, but it's very hard to detect. Right, so, and here we go, move on to the P side. So the P side, we actually have, this is what I've been working with more closely, so I'm a bit more familiar with this. But we actually have, as well as trying to find defects, we also want to find certain markers that can then be used for processing or sort of aligning the predictions exactly with where the sample is on the microscope. And you can see this one we also do very nicely. We detect, detecting these is fairly easy, but we detect a lot of the defects, especially. Although we do have a bit of a problem with multiple detections on this. Especially here, you can see we have lots of them, and that's basically because of the way when we do the sewing together at the edges, it's kind of a bit, sometimes it's a bit ambiguous, but this is a problem we can solve. So more different kinds of examples of these defects, and that we can see them quite easily. Yes, the facets are quite well done now. As on a level of metrics, we get about we get a F1 of about 0.8 on the facet and about 0.6 on the 0.8 on the P side and 0.6 on the facet, and that's probably mostly by these crowded areas that we miss a few in. That's about it. That's almost about it. I was a bit paranoid about going over time, so I think I've overcompensated. But so basically object detection is kind of quite a nice thing for this kind of defect detection. And we still have some failure cases, but I think they're normally good enough that we can accept or reject a sample. I think FBI also want to use these for statistics of the type of error classes they have as well, and in that case maybe it's a bit more important to clear these up. And we also have some extensions, so we would like to move to semantic segmentation because it gives you a bit more information about the defects and where they are, but it's a bit easier to train. The difficulty is that it makes the labeling even more painful, and I think many people have experience with dealing with labeling data here, and it's quite a mess. It takes a lot of sort of expertise, and it's like very tedious. We'd also quite like to experiment with wrapping it in an active learning environment again to help with the labeling, so you could sort of incrementally train it. But I think there's some danger there that this can be misleading. If you start making mistakes, the active learning can sort of reinforce them and make you make the mistakes more often. So that's something to be a bit careful of. That's about it.
Thanks a lot. Any questions?
Thanks, very nice talk. So one thing I'm usually wondering, any specific reason why you chose RTNN and not something like YOLO or?
Well, basically, so I would say not especially. We could have used YOLO. We could have used a lot. There's more modern stuff like DETA as well. We used it because it was fairly common in the literature we looked at, and also, obviously, this is quite a, I don't know, quote unquote simple problem. That the defects are not so abstract. So we were kind of able to mess around and artificially sort of truncate the network and take some earlier things in the way that. So this was a bit easier to play with. As to why we use deep learning over sort of classical computer vision, which I assume is a natural follow-up question, we actually did experiment initially with classical computer vision. It works very well on these, as you could understand. We had a simple model where we just found the median color and looked at the distance from that, and that finds defects reasonably well. I think it struggles with, it would struggle with this, but it finds them reasonably well. The difficulty is then classifying them. And, so we have, one of our partners, DLS, actually has some quite tight computational restrictions, and we're kind of trying to extend this classical computer vision approach. So we would have use this median color distance to find proposal areas, and then classify them with just a binary classifier. On the facet side, this structure is kind of just enough to sort of frustrate most attempts. What we are looking into is getting the sort of CAD blueprint designs that are used to make these, and comparing, and then maybe trying to do some more experiments with classical computer vision there. That's quite difficult because the format is in some sort of slightly arcane, not quite proprietary, but quite hard to use data format, and we also need to, it also means we need this is obviously a small part, or two small parts of quite a big end-to-end pipeline that FBI are putting together, and that means we need additional data inputs to that, and that could cause some hardware problems. The other difficulty is, of course, the reason we're detecting this stuff is because the exact alignment isn't quite known, and we would like to, and then, so if we did have these, if we did get even if we could import easily these blueprints, we still need to align them. And I think there's maybe a risk of getting one bar out quite easily there. But yeah, we have looked at classical computer vision. It's just the best performing approach at the moment is this faster RCNet.
Yeah, thanks.
Thank you for your talk. I'm interested to know how this translates into like saving money or something.
Yeah, so basically, yeah, the throughput here is not huge. These are quite small, and these are quite expensive. I think it can depend a bit on the sort of how they're tuned, but in the most expensive case, each one of these bars can be 2,000 to 3,000 euros. So, and they're very small, so it's not huge. Throughput, I think the main uses for this are sort of to help a human quality assurance person rather than replace them, and also to help get statistics on the errors. So, for example, these small ones are dots, and I think if there are too many of those, that's an indication that the temperature of the furnace is too high. So by sort of, even if you're not necessarily using this as a gating, there's a advantage to automating it because it lets you look at these statistics a bit easier rather than having to go through and label them. Because it's easy to look at this and see that this one is not usable, but a human would have to label all of them if you really want to look at the statistics. Yeah, thanks.
Thanks.